You know, for centuries, we've faced down some truly deadly viruses. We've even managed to completely eradicate some, like smallpox. But there's this one virus that just keeps coming back year after year, a constant, nagging reminder of nature's persistence. Today, we're diving deep into the enduring, ever-changing mystery of influenza.
It's a fantastic question, right? On one hand, we defeated smallpox, a virus that killed an estimated 300 million people in the 20th century alone. Total victory. But the flu, something that feels so common, it remains this persistent global threat. The difference isn't our technology, it's the virus's incredibly unique and honestly brilliant evolutionary strategy.
And believe me, it has absolutely earned that title. The flu doesn't just cause seasonal misery. Its most dangerous form, Influenza A, is the only type we know of that can cause these devastating global pandemics. It is a relentless, recurring threat on the world stage.
And if you want to understand the stakes, all you have to do is look back to the 1918 pandemic. The estimates say it caused up to 50 million deaths worldwide. So yeah, this isn't just a bad cold. This is a virus with a truly formidable history and a capacity for immense destruction.
Okay, so to figure out why it's so darn successful, we've got to understand how it works. We're going to pop the hood, break down the virus itself, and see exactly what happens when it gets inside our bodies.
At its core, the virus is just elegantly simple. It's really just a little bundle of genetic material. In this case, 8 RNA segments, all wrapped up in a protective shell. But the key to its success, the real action, is on its surface, these protein spikes that act as its tools for breaking and entering our cells.
The two most critical tools here are proteins called hemagglutinin, or HA, and neuraminidase, Na. The easiest way to think about them is like this. HA is the key. It's shaped to perfectly bind to the outside of our respiratory cells, basically tricking them into letting the virus in. And then there's Na, which hacks like a tiny pair of molecular scissors. That becomes super important a little later on.
The whole infection process is basically a 4-step heist. First, that HA key binds to one of your cells. Then, the cell gets tricked into swallowing the virus whole. Once it's inside, the virus releases its RNA, which makes a beeline for your cell's nucleus and completely hijacks its machinery to make thousands of new viral copies. These new viruses then bud off the cell's surface, but they get stuck. And that's where the Na scissors come in, snipping the new viruses free so they can go off and infect countless other cells.
So we know how it infects us, but that doesn't explain its incredible staying power. And that brings us to its real secret, the evolutionary genius that makes it a brand new threat, season after season.
I mean, how does it do it? How does it keep evading our immune systems, which are literally designed to remember and destroy returning invaders? Well, the answer lies in its amazing ability to change its appearance.
The first mechanism is something called antigenic drift. Remember how the virus makes thousands of copies? Well, its replication process is sloppy. It makes these small errors, kind of like typos in its genetic code. Over time, these tiny little mutations build up and they change the shape of its HA and Na proteins just enough that our immune system might not recognize it perfectly from one year to the next. Then there's the second, much more dramatic mechanism, antigenic shift. This can happen because the flu's genome is broken up into 8 separate segments. So if 2 different strains, like say a bird flu and a human flu, infect the very same cell, those segments can get all shuffled up and repackaged. This isn't a typo, it's a complete rewrite. It creates a totally novel virus subtype that our immune systems have never ever seen before. So let's just lock this in. Drift is the slow disguise, the thing that makes the virus a constantly moving target year after year. Shift is that sudden transformation, the thing that creates a brand new threat almost overnight. And look, these aren't just abstract science concepts. Drift is the reason we have a flu season every single year. And shift, that's what can lead to pandemics. The 2009 H1N1 swine flu was a perfect example of antigenic shift, a new combination of genes that the entire global population had very little immunity against. This constant evolution forces us into a purely reactive position. We're in this endless, high-stakes race against the virus. It's a chase that pretty much defines our entire public health approach to influenza. Because of that antigenic drift, the immunity you had last year, whether you got it from a vaccine or from being sick, it might not be very effective against this year's circulating strains. So the vaccine has to be totally reformulated every single year to try and match the strains that scientists are predicting will be the most common.
And that schedule is incredibly tight. The World Health Organization has to make an educated guess way back in February about which strains will be dominant more than 6 months later during the next flu season. That long lead time is absolutely necessary for production, but it means they're aiming at a moving target months and months in advance.
And sometimes that guess is off. A great example is the 2014-2015 flu season. The main H3N2 virus, it drifted significantly after the vaccine strain was already selected. And the result? The vaccine was only about 19% effective that year. It's just a stark reminder of how tricky this virus is to predict.
So what about treatment? If you do get the flu, we have antivirals. The most common one is oseltamivir. You probably know it as Tamiflu. It actually works by blocking that NA protein, those molecular scissors, and that stops new viruses from being released. But it's not a cure.
So what's the actual trade-off here? Well, the data shows oseltamivir can shorten your symptoms by about a day and lower your risk of complications like pneumonia, which is good. But here's the catch. For it to be effective, you have to take it within 48 hours of your very first symptoms. And for some people, it comes with side effects like nausea. You can see how this annual chase against a mutating virus, it's just not sustainable. And that's why the holy grail of influenza research is to find a way to get ahead of the virus, once and for all.
The consensus in the scientific community is crystal clear. We cannot keep playing catch-up. The ultimate goal is a universal vaccine, a single shot that could work against most, if not all, strains of influenza. And the approach is brilliant. Instead of targeting the constantly changing head of the virus, those HA and NA proteins, a universal vaccine would go after parts of the virus that are stable, parts that don't really mutate much between different strains. This could give us broad, long-lasting protection and potentially end the annual vaccine scramble for good. It really is the ultimate question in this long battle between humanity and influenza. The virus has a brilliant strategy for survival, one that's built on constant change. But with the pursuit of a universal vaccine, researchers are literally trying to outsmart evolution itself. The hunt is on for that final master key.